Sorry. Okay, so welcome to this lecture on dynamical systems. And this will then more or less finish our part 2 of the lecture. This is now the part which is going away from stochastic dynamics and is dealing with the deterministic view mainly. Okay, so let's go into details with this. The question is, what is a dynamical system? What is the kind of thinking? And you will see that actually we will, not in this lecture, but sometime in future you should see that there will be a lot of relations, connectivities to stochastic processes, which we discussed earlier. So if you want to understand the dynamical system, the first thing is you need a state space. This was exactly the same as with our stochastic processes, and also if you remember the rule-based systems, if they had numerical rules, then they also had state spaces which, if you could count the particles, were integer valued, or if you had substance or fields, then they were real valued. So you have a state space, and as we will see, it is very important that you have a notion of distance in that space. So we assume here always that the state space denoted by S will be a Banach space. Now the next thing is, of course, we also have time. This is also exactly the same as in the stochastic processes. Again, we have the same notation, so we have a time set which we denote by capital T. I will come back to that in the next slide. And now the next thing is, this is a little bit different, but actually you will see that you could define something similar also for stochastic processes. Well, here you have an operator which we call phi t. And you see it's indexed again by the time set t. Remember also the stochastic processes were indexed by time t. And this operator is acting on the state space S. So we will write, at a certain time t, we are acting on an element S in S of the state space. And if we go now, through different times, we will create a so-called trajectory, which has, for example, as an initial condition, some element S in S. So these three things here you need to define properly, and this we will do in a definition very soon. You need these three things in order to define a dynamical system. Excuse me. Okay, so let's discuss a little bit the time set t. The time set can be of the following type. Actually, we could have already said exactly the same for stochastic processes earlier in an earlier lecture. So we can have either a full time continuous dynamical system. In this case, we set the time set just to be the real numbers. If we only go in forward time, which also sometimes can happen, then we take t to be the non-negative real numbers. The same is true for discrete dynamical systems. So if t is given by z, we have a full two-sided discrete time dynamical system. But of course also here we can have only the idea that we move only in forward time, and then we would take the the non-negative integers. Okay, so we have to introduce some really basic notions that are important in dynamical systems theory. So the first thing is, if we look at some element S, we can define a forward existence times t plus of S, and this will be the time how long the trajectory exists inside S, of course using this operator which we have looked at in the previous slide. And similarly we will also need in some cases a backward existence time, and this will be denoted by t minus of S. Right, now you can define a trajectory a little bit more precisely, because now we can look at the operator phi t of S, and if and S now will be the initial condition, so we start at S, and now we can move in forward and backward time, and this will exactly define us the trajectory which we have. And we also assume that there is some neutral element in the time set, which we will always denote by 0. And this has the property that if you apply this point of time to S, then nothing happens. So phi 0 of S is equal to S. And now we can define the whole existence time of any element S in S, and that is given by J of S, and that will be just the interval t minus of S to t plus of S. So how long you can go in backward time and how long you can go into forward time to define the trajectory. That is the set J of S. We will also sometimes need the so-called extended state space. This is usually given by omega, or denoted by omega, and this is just the union over all elements in the state space of the existence times the element itself. And then we can see that we have that this operator phi is actually a mapping from this extended state space omega into the state space S. So we are now ready to define dynamical systems properly. So consider the triple S, T, and phi, where S is some set called the state space. Remember, S was had also a Banach space structure. T is the time set, and phi is a group of transformations of S indexed by T, and we now call it the shift operator. That is telling you we are shifting states in S with this operator. But it must, this operator is assumed to have to follow, that the following conditions hold, and that is C1, omega must be an open set in T times S. Secondly, we require that phi is, as a mapping from omega to S, is continuous. And then we have this neutrality condition, so C3 just says if we apply the 0 element of time to the operator, then nothing happens. We just stay at S. But now C4 is the most important condition here, which we have to understand. So let's just read it first. So for S in S and some time t prime in the existence interval of S and t in the existence interval of phi t prime of S, we have that also t plus t prime must be in the existence interval of S, and with that it holds that the operator phi t applied to the operator phi t prime, which was already shifting element S, must give you exactly the same result as if you just take the operator phi and go over the whole time interval t plus t prime of s. So what you have, in other words, is the following. So you might start here at s somewhere, and then you shift along with the operator until you come to another point in state space. So the whole thing here must be inside the state space, which is given by S. And then you shift a little bit further. So this here was taking up time t, and here this was taking up time t prime. And now you say, you could also have, instead of stopping here, which was the condition given here on the left-hand side of this equation, so instead of stopping here and then going up here, you could also have gone the whole way through just in one go. And this is exactly what is here on the right-hand side. And if this condition is now satisfied, then we say the triple ST phi is called a dynamical system. Okay, so we have the proper definition now. With this we can rewrite a little bit more in a more simple way what trajectories of the systems are. So we make this basic notation here that t times s, so this is, we say t applied to s, t on s is given by the shift operator phi t applied to s. So this is a much simpler notation. The trajectory through s in s can therefore be written as t is mapping to t times s. We define the forward orbit gamma plus of s as just the whole shift from the zero element up to the existence time t plus of s applied to s. So we shift all the way until we can do that no longer. Of course, in principle, t plus of s can be also infinity, so we can shift forever. And the backward orbit is defined similarly. We just, in this case, of course, shift backwards. So we can use all the shifts for all the backward times for which the orbit is defined. And then the whole orbit going through s, gamma of s, is defined just as the union of the forward and the backward orbit. With this simple notation, we can, for example, very easily define equilibrium. So a state S in S is called equilibrium or critical point if and only if we have that t times S is S. So whenever we apply a shift to the state S, we stay in S, and this must hold for all times t in the existence interval of S. Actually, you can already see, if this condition holds, then actually the existence time of this trajectory is infinity, because you can shift in forward and backward time as much as you like. You will always stay on the same place. So in this case, we have that the orbit is just given by one single point, and that is S itself. A little bit more complex constructions are periodic orbits, and they are also, of course, very relevant in mathematical modeling for all kinds of periodic processes. So we say the set P, P, a subset of the state space S, is called a periodic orbit if and only if for all S in this orbit P there is a small p not equal to 0, which we call the period, and such that, if you apply now the time t plus p to S, then you are exactly back at the same point, so that would be the shift t times S. This must hold for all t in the existence interval of s. And also all the points must be on the orbit. So the whole set of the orbit is defined such that you can go from any point to any point. So there is a t prime in t such that for all ss prime in the orbit p, we have that s prime of t is t prime times s. So of course a typical example of an orbit is something like that. Maybe you have seen that. So we would have that. This is the orbit P, so all points here. This, for example, could be S. And now if you shift S around the orbit, you come back to S eventually, and you have here that you have here of course that P times S, so you're shifting S with a period S must of course then exactly be S. A very important, maybe the most important two-dimensional system, orbit for a two-dimensional system is the harmonic oscillator. What you have here is R2, and you start here with some initial condition here or here, and then you go around the orbit, and for every initial condition, for example here on the y-axis, so if this is x and y, you come back to the same point. And so the solution of this underlying differential equation is are just concentric rings which fill up the whole of R2. Now let's go to stability. So what we want to understand that something is stable. This will be as follows. So we have the following. So we say a critical point S star, and S is called stable if for any neighborhood U of S star there exists a neighborhood V of S star and a tau in the existence interval of S star, such that if you shift t plus tau times xi, this must be in the neighborhood U for all t from 0 to t plus of xi, and that is for all xi in the neighborhood V. Okay, so this looks a little bit like, for example, the condition of continuity, which you have learned in year 1. So, but it's good maybe to illustrate that. So what do we have? Right, okay, so let's draw this a little bit. Say this here is the state space S, and this here is time. And here, let's say we have the element S star in the state space S. Now, of course, if we would start exactly on S, then we would stay there for all times. So that is not a problem, but now we introduce our neighborhood which we called V. So let's do that. So we have here our neighborhood V, and then we have an even bigger neighborhood which we call then u. And the condition says, so we start at some point xi, let's say xi is here, and we have to introduce this time tau. So up to time tau, yeah, and of course I have to draw here the two neighborhoods v and also u. So we start at xi, and up to time tau we are relatively free about what the trajectory is doing. So we could have, something that is going like this. But eventually, because we started in v, we must have to remain in u. So this could look like this. Yeah. So that is stability. Okay. But now we have one more property, and that is attractivity. So a critical point S star in S is called attractive if there is a neighborhood omega of S star such that for xi and omega we have t plus of xi is infinity, so the existence time must be for all times. And we have that the limit t to infinity of t times xi is exactly S star. So that means, in other words, if we draw that, so we have here somehow our point S star, and we have here our neighborhood omega, say a little ball around it, and we start here inside. And now, first we could have anything. So we know the existence time for all these xi's is infinity, so we can go on forever. So we could actually first or even leave the neighborhood omega of S star, but eventually, because the limit must be S star, so eventually we must actually converge to S star. Okay, so this is attractivity. It's interesting to note that the definition of stability of equilibria and the definition of attractivity of equilibria are independent from each other. So you can have critical points that are, for example, stable but not attractive. Actually, one example I did draw previously, so if you look, for example, here at the harmonic oscillator, then you see that every such orbit is stable, but of course they are not equilibria, but you can also introduce stability for orbits, and then they would be and then of course this here is an equilibrium even. So if you take this as S star, then you can take any neighborhood here to be one of these orbits, and then you would stay there for all time. Therefore S star clearly is stable, but because none of these orbits actually converge to S star, therefore S star is not attractive in this example of the harmonic oscillator. Okay, but if you finally have that if S star is an equilibrium and is both stable and attractive, then S star is called asymptotically stable. Yeah, and now I should tell you the principle of linearized stability, because this is very important for ordinary differential equations. So there is one principle that actually tells you whether an equilibrium for an ordinary differential equation is stable or not. So let's look at let's look at an ODE. So let's say we have a state space X of x1 up to xn, say xt, say. So we have the state space S in this case is given by R to the power D, d-dimensional real space. And we have a system of first order ODEs, so we have d to d xi is given by fi of x, and we have also an initial condition, xi of 0 is given by xi 0. So this is an initial value problem. And yeah, the vector field that is defining this ODE, so is F is a vector field that also has, of course, to have d many functions, f1 up to fd. And the coupling, of course, in this case is through the right-hand side. So here we have x and not xi. So here the whole state x can actually be can be the one on which each fi is dependent on. Okay, and now you define the Jacobian at an equilibrium. So say, so say we have an equilibrium which we call now in this notation x star. And now we can define the Jacobian of the vector field f evaluated at x star. So we can have the the Jacobian. Let's say this is called JF evaluated at x star. So this is a matrix, of course, that has all the partial derivatives of f inside with respect to all the different states x. And now if we have that the real part of this of the eigenvalues of these of this matrix, so if if sigma of JF is negative, so the real part of that, then we have that, and that of course must be evaluated at x star. Then we have that x star is, so here sigma of course is the spectrum, so contains all the eigenvalues of the matrix, of the Jacobian matrix. And then x star is actually so-called locally asymptotically stable. So in other words, you can know from the linearization of the system, this is the linearization of the system which gives you the Jacobian matrix, you can actually, from the spectrum of this, you can conclude that a certain equilibrium in this system is locally asymptotically stable. So this is a very simple criterion on stability, and yeah, therefore this is the principle of linearized stability might actually be one of the most important theorems of applied mathematics, because it is immensely important to know when equilibria are stable or not stable. Right, okay, so let's continue. So we go to limit sets. A limit set is defined as follows. So we have a state space S in S. We have a state in the state space S, And then omega of s is defined as here the intersection over all positive times of the closure. So I should actually give you this notation. So this bar is the closure in the set theoretic sense. And you look at the closure of all forward orbits gamma plus when you do the shift until time t of s. So maybe an illustration is in place. So you would have something like an equilibrium, say, which is locally asymptotically stable. This is always a good illustration first. So let's say this would be S star. And you would somehow start there at some point S prime. And then, you would follow this trajectory, taking the shift operator. And then let's say that S star finally converges to S star, so S star must be locally asymptotically stable or asymptotically stable. And now what is this construction? So we would have in this case actually that omega of S prime is actually S star. Why that? Well, we can illustrate that. So we do the shift along the trajectory, let's say until here. And then, here we would stop. And then we take the intersection, and then this whole part here is taken away from the orbit. Then we go a little bit further, stop here, and this, because of the intersection, is taken away. So we work our way forward until we come very, very close to S. And you see, we cut always away the whole orbit, but not S star itself to which it converges, because we have taken here the closure. And of course we can also do the same construction in backward time. You should do some illustrations for yourselves, and this will then define you the alpha limit set of a certain point S in the state space S. Now with this we can actually define attractors. So a point S in S is attracted by the set M subset of S if t plus of S is infinity, so existence time is forever, and we converge in time towards this set M when we go with t to infinity. So you can, in other words, what I do here is you can have somehow a state space S, and then you take out an arbitrary subset here, call it M, and then you look at some point S, and then if by the shift operator, which is defined by the dynamical system, you would actually converge towards M, then you say that M is attracting S. And with this you can now define the domain of attraction. So the set A of M is then defined as the set of all S in S which which is attracted from M. And this is called the domain of attraction of M. And the set M is called an attractor if it has some elements of the state space S which it attracts. And if it attracts actually all elements of the state space, so the whole state space will be shifted towards M, then this is called a global attractor. Okay, now we go to our most important examples in the lecture, and these are the rule-based systems. And now we give actually a dynamical systems interpretation to the rule-based system. So I discussed this here for particles which can be counted first. So we first introduce a concentration xi, which is the particle number which is in in the area of a certain type. We have drawn this classification of the object set several times. So we define here a concentration by the particle numbers per volume. And for that we want to write down a differential equation. But we have a little bit to work for that. In reality, which we don't do here, what you really would need is a continuum limit. And this would, this would be a limit where each of the ni's, so the integer state space, which says how many particles there are of type Ti, all of them for each type would need to go to infinity. So the continuum limit would be something where we take ni to infinity for all i's which are according to our notation between 1 and s, because we always assume we have s many different types in the system. So we have our vector of concentrations now, which is associated to the rule-based system of equations. And with that definition, I would like to give you the same definition as we had before, but now we do this for deterministic dynamics. We have dynamical systems, so we have exactly the same kind of setting. We have again many different rules in the system. We have the same three requirements: how the complexes, the types, and the rules are behaving. And so if we have this definition now with an update which is now deterministic, so the update rule is that all the rules are constantly applied all the time in the system. That is our basic assumption. Then this will be called a rule-based dynamical system. Yeah, now we have to introduce what is usually called mass action systems in the literature. So let's write it down. The reasoning is very simple. So you assume, again, you have collision update in reality. So, you have S is a kind of reaction, where our state space is a reaction volume, and you have here, let's say, particles inside of different types, and sometimes they bump into each other and give changes in the concentration. So now we are talking about concentrations, not particle numbers anymore. And the mass action system is averaging heuristically in the following sense. So we assume that the change of concentration is proportional to the concentration of the particles in the system. So the higher the concentration, the more, the faster the reaction should take place, because there are more underlying collisions. But here, of course, the collisions are taking place all the time. There's no discrete event structure here anymore. This is actually very important to notice as a difference to the stochastic process, which were defined via the collision process in the rule-based stochastic systems. So we introduce in this case here now reaction velocities. They are usually called V. And the reaction velocities will be dependent on the reaction rates, K. So here we assume we have this constant weighted rules or reactions. So for over each reaction arrow there is exactly one kinetic constant. So K 1 to Kr are the many kinetic constants which we have in the system. So the reaction velocities are a vector. They form a vector of dimension r. And they are defined as follows. So this is now very important. This is something you should really learn by heart. So the reaction velocities are given in the following way. So each reaction Rj, remember we had R many different reaction or rules. And we denoted them by Rj. So to each of them we associate now some Vj, a reaction velocity, to each of them. And this is defined here. So we take the reaction constant Kj times now the product. So that is I goes from 1 to S. We have S many different types, or chemical species in a reaction system, for example. And here we take the concentrations of each species, xi, we have defined this in the previous slides, to the power of the stoichiometric coefficients in rule Rj of the source side of the rule or reaction. Maybe I should actually change the notation here slightly. So instead of gamma ij, actually we did take earlier the notation alpha ij. So we have here the concentration xi to the power alpha ij. Well, does that make sense? It does actually, because, for example, if you have a reaction where, let's say, two particles, two green particles have to bump into, let's say, one red particle. So they form here a reaction by all bumping into each other. Then you see that on the source side you would need two green particles and only one red. So the velocity of this reaction would actually be something like a constant. So you would have this Kj, and then you would have let's say the concentration of the red particles are given by x1, and then the concentration of the green particles would be x2. But now, because you need two of these particles to create a new to create a new product, this would actually be to the power 2. So you see, you can interpret here the reaction rates as proportionality constants. And then the mass action assumption tells you that the concentrations to the power of their stoichiometric coefficients on the source side are giving you the reaction velocities. Of course, remember, if something is not in reaction or rule Rj, some of the types are not present to form new particles on. So if they are not present on the source side of the rule or reaction, then you have here concentration xi to the power 0, because the stoichiometric coefficient would be 0. So that would give you a 1, and therefore it would not contribute anything to the reaction velocity Bj. So we can actually assemble all these reaction velocities together, and then the rule-based dynamical system is defined as here. So this is now in a vector notation. So you have here the whole vector of concentration d to dtx is given, and this is now immensely important. So you have here the stoichiometric matrix. Remember, the stoichiometric matrix gives you the net production of certain types in the system. So that makes sense that the stoichiometric matrix should appear here in the definition of this first order systems of ODE. And then also see that you also have to check this, that the stoichiometric matrix has exactly the right dimension. So you can multiply it with this r-dimensional vector of the reaction velocities v, and this exactly gives you then the first order differential equations describing the rule-based systems with in a dynamical systems interpretation. Of course, remember that we also had cases where we have more than only constant rates. In this case, we can generalize the definition of reaction velocities, and we just, instead of constants, we write here the functions which are on top of the rule arrows. So we call them function-weighted rules. So these functions just appear here in front of the product as replacing the reaction constants we had before. Yeah, so this is indeed the definition. So we have a general dynamical system which is based on rules with a function weight. So you write here, instead of the r many reaction rates, you write here the r many functions that are weights on the rules. So let's finish this lecture by applying this definition of the rule-based dynamical systems to some of our examples which we had looked at before. So remember now the simple cell cycle model, which is, I just have rewritten here all the reactions that defined the cell cycle model. And if we now exactly use the mass action kinetics hypothesis, then, and also using some conservation relationships which we have assumed for this cell cycle model, then you end up with a system of 3 first order ODEs, where all these different concentrations, that are the concentrations of MPF, CDC25 and mitosis factor 1, are given by small m, small c and small t. Yeah, and a little bit with a relabeling of some of the constants, and getting rid of some of the variables which are actually constants due to the conservation laws. You can rewrite the whole system in the following way. So these are typical techniques employing conservation laws to make the system a little bit simpler. This is something you should always have in mind. So we have a 3-dimensional ODE in the end due to the conservation laws, which is describing the cell cycle model. And we have 6 parameters here from K1 up to K6. Sorry, we have actually 8, 9. We have 9 different parameters. Remember here, the parameters are defined as previous parameters, but times the other concentrations which you can get rid of due to the conservation laws. Okay, but now we also want actually to use mass action kinetics for rules which are using substances or fields or energies. So we look back at our simple market model. Remember, these have been the different rules you have for this market model, but now remember that the state space of the system is actually real valued, not integer valued. But this, of course, you don't see later in the concentrations. But the concentrations are also defined as before. So you have substance per volume is giving you a concentration in this interpretation. Yeah, you do exactly the same construction as for the particle systems. So you have first to construct all the different stoichiometric net production vectors n1 to n5, and then you can actually assemble the whole stoichiometric matrix, which now looks like that. Now you can see that here you have not only, of course, integer values in the net production, because you have also real valued stoichiometric coefficients. So if you look at here, for example, these are clearly non-integer values, entries into the stoichiometric matrix. It's very important to note. And now if you just formally plug that into the mass action kinetics formula, then you get this model here, and this then can be simplified to a two-dimensional ordinary differential equation where we have redefined a little bit the parameters. So we assume here that psi is between 0 and 1. We have a new parameter beta, which is given by gamma plus alpha. We have a new parameter kappa, which is given by mu plus sigma. So look again at this equation. You see all these parameters are well defined, and also the state space is well defined. It's two-dimensional because C is the concentration of capital, so to speak, in the system, and E is the concentration of economical size in the equation. Yeah, and the interesting thing is that actually, and this is how I constructed this model, this is actually a model which satisfies the so-called general equilibrium theory, which is a very old theory stemming from the 19th century, which is essentially assuming that the market is always in equilibrium. And actually you can prove that there is such an equilibrium. And you can also, of course, then investigate under which conditions this equilibrium is stable. That's also an interesting question, because if, for example, we could destabilize this equilibrium and it could, for example, start to oscillate, then we could go away from a general equilibrium market where we assume that after small perturbations the economy always goes back into equilibrium state, and we could, for example, have market cycles where we have a certain oscillation over time of both the capital and also the economic size. And you should actually check that this is possible. Actually, it seems possible that we can destabilize with some of the parameters, and of course you have to be then you have to make sure you understand the interpretation of the parameters. but then we can possibly destabilize the unique equilibrium we have in this market model. So we are at the end of this lecture 11. Let's just go to the conclusions. So we have in this lecture encountered we have understood what is a dynamical system. We also gave an introduction to stability and attractors of such dynamical systems. Then we had a very important step for this lecture. And this is, we had an interpretation of rule-based systems as dynamical systems. So with the help of the mass action kinetics, we can transform rule-based systems into dynamical systems. And from now on, you should practice this as much as you can, how to derive a dynamical system from a rule-based system. And you have two examples already, and that was the cell cycle and the simple economic model. Okay, so this brings us to the end of lecture 11. And yeah, I say goodbye.